Here we are at example 6, but before we dive into that example, we're going to go ahead and look at the definition where polynomials are continuous everywhere. In the past notes, we've actually seen like a really quick definition of it, but this is really kind of the formal definition as to why things are working in that manner. So as long as p of x is a polynomial, then it has to satisfy three conditions, and they are very, very similar to the three conditions that we've actually already seen in the past. The first one is that p of x has a domain going from negative infinity to positive infinity. In other words, if you were just to draw a quick sketch, we could see a function going on and on and on forever and ever in both negative infinity and positive infinity for your x values. So that is the first one. The second criteria, is that the limit as x approaches some a value of our polynomial function exists for all a values. In other words, in fact, let's do a better graph so we can kind of illustrate these points. So the first one, again, we are ranging from negative infinity to positive infinity. Let's just say that this is our polynomial. We're going onwards. Again, that's the first criteria. The second criteria is the limit as x approaches any a value. So I could let my a value be right here. Notice the left side is in fact meeting up with the right side. That's just any particular a value that I chose. Here might be another one. Notice the left side is in fact meeting up with the right side. And then another one might be like out here. Again, left side meeting with right side. So this exists for all a values, every single one. The third criteria is that they end up meeting. So the limit as x approaches a of our polynomial function is in fact equal to p of a, much like a lot of the continuity criteria from before. All right. The limit as x approaches a is in fact meeting up at that same point when you plug in a into the function, that polynomial. So as a result, all three criteria then have to be met for this polynomial to be continuous everywhere. Now, how this is going to help us with example 6 is we're trying to show that this function, the absolute value of x, is in fact continuous between negative infinity to positive infinity. Now, this gets a little trickier because we actually kind of have to do like a basic short proof, but it's definitely potentially like free response AP type questions. So it's definitely good to know how to prove something is continuous. So if we have, let's just go ahead and draw a rough sketch of what the absolute value of x is. Here's my x and y plane. And we know that the absolute value of x is simply just a v that opens upwards. So we've gone ahead and drawn that function. Let's go ahead now and write out what this function, the absolute value of x, is in terms of actually a piecewise function. And the reason why we're doing it in terms of a piecewise function is actually going to help us out in kind of proving this thing. So as you can see, just looking at values larger than 0 or equal to 0, so x is just larger than 0 or equal to, we have this line y is equal to x. So again, we're kind of omitting this whole left side for a moment. But it has that line y is equal to 1x plus 0. In other words, things are in y is equal to mx plus b form. All right? So it has this line y is equal to 1x. Alternatively, anytime that you are less than 0, your x values are less than 0, we're looking at now this part of the graph, we're ignoring this right side, we're just looking at this guy. We see that we have a slope of -1 x, and it does have that same y-intercept of 0. So what we've done is we've taken the absolute value function and written it as a piecewise function. Now, for criteria 1, the absolute value of x, which again is equal to our piecewise function 1x as long as x is larger than or equal to 0, or negative 1x as long as x is less than 0, it does in fact have a domain ranging from negative infinity to positive infinity. We could even see that specifically from our graph. These arrows will go on forever and ever and ever. And likewise, from the piecewise function, x values are going up and up and up. X values are going down and down and down. So criteria 1 is met by saying that the domain is going from negative infinity to positive infinity. Now let's really go ahead and take a step back and look at this piecewise function individually. So for x's, so this is for criteria 2, for x's being less than 0, then we have the limit as x approaches a. But again, since we're talking about x values less than 0, we're specifically talking about maybe a negative a value. So that's why it's important for this limit to have that negative in there. Of the absolute value of x is equal to then the limit as x approaches negative a of, really again, from our piecewise function, we're only dealing with values, or x values less than 0, we would follow this portion from our piecewise function, negative 1x. And as a result of that, anytime you throw in that negative a for x, we end up with negative 1 times negative a, which simply comes out to be a positive a. So just a really quick example of this would be like the limit as x approaches negative 2 of the absolute value of x. Well, that's equal to the same thing as saying the limit as x approaches negative 2 of negative 1. Now going ahead and using that direct evaluation. Oops, this would still be negative 1x. Jumping ahead. And thus giving us then a positive 2 when you throw in that negative 2 value in there. So again, that's just a really quick example of how that's interacting. Now likewise, let's see what's going on when we're approaching 0. And again, that was a negative value that we were throwing in there. Just another side one, the limit as x approaches 0 from the left side of the absolute value of x is equal to the limit as x approaches 0 from the left side of negative 1x. Well, that's the same thing as saying negative 1 times 0, which is just 0. So kind of also looking for that continuity to show that they do in fact meet up at that value 0. So those were values that were less than 0. Now let's look at things that are larger than or equal to 0. So for x's being larger than or equal to 0, then we have the limit as x goes to, in this case, any positive a value, because again, we are to the right side of our, we are on the right side of our piecewise function, dealing with x's that are all positive, of the absolute value of x is equal to the limit as x approaches some a value. Now, again, dealing with that piecewise function, since we are in the positive x values, we just have that positive 1x from our piecewise function. Again, just coming from right here. Well, going ahead and throwing that in there, we end up with 1 times our a that we had, which just comes out to be a. Just a quick example of what this could look like is if we had the limit as x approaches, let's just go with 3 this time, kind of differentiate the numbers, of the absolute value of x. Well, that's equal to the limit as x approaches 3 from our piecewise function, 1x, which is equal to 1 times 3, which is just equal to 3. Now again, trying to verify that those meet, the left side does in fact meet up with the right side, let's go ahead and show what's going on as you approach 0 from the right side. So we end up then with the limit as x approaches 0 from the right side of the absolute value function of x is equal to the limit as x approaches 0 from the right of 1x, which is equal to 1 times 0, which just comes out to be 0. So they do in fact match up. So that's a good sign that they are in fact matching up like that. Now comes step 3. So again, we've shown that the limits exist at a variety of different places. Generically, we did the a and the negative a, just to show that they are going anywhere, that they work at any a. Now looking at step 3, we can verify that for any for any a that's inside of this interval negative infinity to positive infinity. This, by the way, is an element of. Is an element of. In other words, this a is in between negative infinity and positive infinity. It's part of it. Then the limit as x approaches any a for this absolute value of x function is equal to f of a. And as a result, since we have verified all 3 criteria, the absolute value of x is, in fact, continuous on negative infinity to positive infinity. So again, just to kind of recap things, we have the absolute value of x. Here it is, that v opening upwards. We just had to show that the domain was ranging from negative infinity to positive infinity. That is criteria 1, and that is very true. You can see the arrows going outwards towards negative infinity and positive infinity. The second criteria were that the limits also existed, all right, for any a. And we could see that they were, in fact, existing. There was nothing here that did not exist. And then finally, for criteria 3, for any a value that's between negative infinity and infinity, the limits of that function, in fact, equaled the actual function when you plugged in any a value that you wanted. And as a result, this function then is, in fact, continuous from negative infinity